Hello guys, welcome back. So in this lecture, we'll be purely focusing on the space complexity. So we'll be seeing like what is space complexity, why we need it, and how we can check like how much space an algorithm is taking, right, to run a code. So we'll start by seeing like why we use it, why we use space complexity, right? So we basically use it to check how much additional memory we need to allocate in order to run our code. Because if you run any code, then obviously it is going to take some memory in your machine, right? So with the help of the space complexity, we just try to get the broad overview, or we can say big picture of how much memory we have to allocate in it. Okay, and this is also something where we can use big O notation, right? So big O is also used, like big O's expressions are also applicable for the space complexity. Okay, and here when I'm talking about the space complexity, so if you think if the n grows, like the space could grow, right? So the size of n, if the n is growing, then it might also take some space, right? So we are not going to talk about that space whichever the input is taking, whichever the input is occupying. Okay, because you guys might have heard about the term like auxiliary space complexity. So what does auxiliary space complexity means? It simply refers to the space which is required by the algorithm itself, okay, except the space taken up by the input, right? So let's say you have wrote a function, okay, there you are passing some input. So if you are passing an input, that input will also occupy some space, right? It will also occupy like some memory in your machine, right? So we are not going to talk about that space at all. We are going to purely see how much space our algorithm is going to take. Okay, so that is why it is called auxiliary space complexity. So whenever I talk about the space complexity, you just have to keep in mind I'm talking about the auxiliary space complexity. Okay, I'm not talking about the space which is taken up by the input itself, right? So now there are some basic rules like which we have to consider while checking the space complexity. Like most of the primitive values, let's say be it boolean, number, undefined, null, are constant space. Doesn't matter how much big number, how much small number you store, they will always take constant space only, right? So they have nothing to do with the size of the input. Okay, so on the other hand, we have another primitive type, that is strings, right? So in strings, there are chances it can grow up to n, right? Because in strings, if you think like we add up the characters at the end or at the beginning or at the any end, right? Like in between also we can add some characters. So its size can gradually grow up to n, right? Up to infinity. That is why the space complexity of string is considered as O of n, big O of n. Okay, so the string size in simple words can grow up to n. Okay, n we can say is a input size. Okay, and same will happen for the reference types. So be it objects, array, or any reference types, they also have the space complexity of O of n, because they can also grow up to n, they can also grow up to infinity, right? That is why we say like if the n grows, like the size of the strings or the reference types can be affected. Okay, so it can be directly proportionate to those. So we are going to see a few examples of it now. Okay, so I think you are now aware of like what space complexity is, what we do in it. Now let's see a few practical examples of it. Okay, so for that I'll go into one of my previous examples. I think I've shown you already one. Okay, so let's pick this one, sum up to n. Okay, I'll just quickly copy it and I'll paste it here. Okay, sum up to n, right? Okay, so I'll remove all these commented code from here. I'll remove this for loop as well. So now we will analyze the space complexity purely. Okay, we will not talk about the time complexity of this code. So what is happening right now here? So we have created one variable. Okay, so it is going to occupy some space in our in our machine, right? And then here in this for loop, we have created one more variable which will occupy some space. Okay, and then what is happening inside this loop? So inside this loop, we are just reassigning, or we are just updating the value of the variable which we have already created. Okay, that means we are not creating a new variable, we are not creating a new memory, right? We are not allocating new memory, we are just updating the value of the already created variable. Okay, so uh, the size of input will not affect this memory size at all here in this case, right? So here we have one memory allocated, here we have one memory allocated. So right now we have something like big O of 1 plus big O of 1, because this one is occupying some space and this one is occupying some space, right? So we can simplify it down to big O of 1. Okay, because if you see, like, even if I pass the 1000 as a input, if the input size is 1000, then also it is going to just update the value of the existing variable. Okay, it is not going to create a new variable at all. Okay, so the size of this algorithm will remain constant. Okay, so the space complexity will be always O of 1, that is constant space. Okay, and we don't have to worry about this memory allocated by memory taken up by the n or input. Okay, because we are going to just look at the algorithm, how much space our algorithm is taking. Okay, or our code is taking, right? That is why we call it auxiliary space. Okay, so let's see another example. Okay, let me just copy it quickly. Okay, so here what I will do, I'll simply loop through this array and then I'll create a variable. Okay, let's say loop value. Okay, and let's store an array in it. So right now I have allocated some memory in this variable, right? So this thing have taken up some space in our machine, right? So what I will do, whenever I'm looping through this number, I'll just simply push that value into the array whichever I have created just now. Okay, so let's just push I. Okay, so now we can return this as well, or let's use this return only. Okay, so now I'll just run it quickly here, right? So I'll pass 2. Okay, so we got 0 1 2. Okay, now I will pass 5. Okay, so it is giving us 0 1 2 3 4 5. That means the size of input is affecting the space taken up by this array, right? So as we are increasing the size of the input, the size of this array is also increasing, right? And that is what I have mentioned here. Like strings or reference types can grow up to n, right? So they are directly proportionate to n, right? In this case, it is directly proportionate to n. So the moment I'm increasing the size of the input, which is this n, it is affecting the size of the variable or the object which we have created, right? This reference type which we have created. So if we pass 1000, then there is going to be the size of this is also going to increase in same amount, right? So for this we can say like the size of this array can grow up to n. Okay, because here we can pass from minus infinity to plus infinity, right? As the size of the input grows, the space will also grow in this case. So here the space complexity will be O of n, right? And we will not consider this one and this one, right? So as we have seen in the previous example, like here it is occupying some space, here it is occupying some space. But these two are not affected by the value of n, right? Value of size of input. So if you want, you can consider, but in the previous lecture, I have already mentioned, like we just simplify it down and we just have a look at the big picture. Okay. So how it will be like O of big O of n, if we consider this one first, and then we have one constant space here. So it will be like big O of 1, and then again we have a constant space here. Okay. So it will also be like big O of 1. Okay. So here we have 2 big O of 1. Okay. So it looks like 20, but you have to think it like it's big O, right? So it looks like 20 right now, and that's weird. Okay. So we have this big O of n plus 2 constant spaces, right? So we are going to ignore the smaller values as we have already learned in the previous video, right? So we just care about the broad trends. Okay, we just care about the fuzzy things, fuzzy trends, right? We don't care about the small values at all, because end of the day it is going to take O of any space only, right? Then who cares about the smaller values, constant values, right? So that is why we ignore the smaller values and we just worry about the broad trends or the big picture. Okay, so that is why the space complexity of this algorithm or this function is O of n, because it is directly proportionate by the size of the input here. Okay, so if the size of the input is growing, the size of the array is growing directly, right? This thing is directly affecting the size of the array. Okay, so in this case it is not affecting it at all. In this case it is not affecting it at all, but inside of this for loop it is affecting the size of the array. So it can go up to n, right? Or we can say infinity. So here we can say as the size of the input is growing, as the size of n grows, the space grows. Okay, the size of the variable which we have created grows, or size of the object or array grows. So it will have the space complexity of big O of n. Okay, so we'll quickly revise it once. Like space complexity we use to like see a big picture of how much space our algorithm will take in order to run properly, right? And here we just talk about the auxiliary space complexity. Auxiliary space complexity is nothing but the space taken up by the algorithm itself. We don't consider the space taken up by the input, because here if you pass 1000, then that 1000 will also occupy some space, right? We don't talk about that space at all. We just purely focus on the space taken up by the function or the algorithm which we have implemented. Okay, so that is what auxiliary space is called. Okay, and then most of the primitive values like boolean, number, undefined, null and constants and null are constant space, but string is one of the primitives which is not constant space, because its size can grow up to n, right? Because it is just a set of characters and we can add as much as characters as we want, right? And then same will happen for the objects and arrays. We can add as much as keys or as much as values as we want in our objects and arrays. So their size can also grow up to n. Okay, so yeah, this is how we track the space complexity of an algorithm, and I hope you guys like it. So this is it for this lecture. In the next lecture, let's just quickly talk about some logarithms. Okay, so see you there.